All right, let's look at some extra problems for AC power. So determine the complex power, average power, and apparent power used by the load in this circuit. Determine the power factor and the parallel capacitance necessary to correct it to unity, or unify it, if you will. Okay, so here we've got a load network, which is all of this stuff. And what we're going to need is the powers and the capacitance that would be necessary to make the power provided to this exclusively real. So to do all of that, what we're going to need is the load network impedance. So this is the same kind of thing that we've been doing for a while when we find load network impedance. Let's get our calculator going here, and what we'll do is first figure out W from the frequency 23, and W is equal to 2 times 3.14159 times F. Okay, so then the impedance of this would be sort of this branch in parallel with this branch, and then that whole thing in series with this. So the total load impedance would be equal to 2E3 plus, we're going to need these two different things in parallel. So we'll have 1 over the first impedance, 1e, so I times W times 1e minus 3, 1 millihenry, plus 800. And then we're going to go 1 over I times W times 1e minus 3, plus 1,000. Okay, so there is our load impedance. And the voltage is equal to just 1, which means the current, so let's call that, actually, let's just convert this to RMS. V RMS is 1 over square root 2, and then I RMS, because we're using the, if we just use the RMS voltage, then we'll compute the RMS current once we take this and divide it by ZL. So there we go. There's our RMS current. Why don't we say convert the RMS voltage to a floating point, and then we've got the RMS current all ready to go directly. Okay, so because the inductances were pretty small, this is mostly real already. It only has a very small imaginary component, really kind of like 4 orders of magnitude. Is that right? 4 orders of magnitude? No, 3 orders of magnitude smaller than the real part. So we don't expect that we're going to have a huge capacitive load in order to correct that out. All right, so the complex power would be S is equal to the VRMS times the conjugate of IRMS, and we're going to get this thing there. So there we go. There's our complex power. Then the average power would be equal to the real part. How do we do this? Real of S? Is that it? Nope, that's not a function. Is it just RE? Yeah, that's the one. Okay, so complex power's real part is the real power, also known as average power. Average power, complex power, and the apparent power would be given by the absolute value of the complex power. So P apparent is equal to abs of S, apparent power. Okay, so because the imaginary part was so small, this is, in this case, almost the same as the real power. Great. Then the now another thing that we should see is if we were to take the RMS voltage, so the kind of amplitude, not the RMS voltage phasor, but the RMS voltage, which would be the magnitude of this, and multiply that by the RMS current, then we would get exactly the same value for the apparent power. Okay, so So let's see, what's next? The power factor and parallel capacitance necessary to correct it to unity. So for the power factor, we can actually compare the real power to the complex power. So the power factor comes from P is equal to V RMS I RMS times the power factor, where the power factor is the cos of theta V minus theta I. And this part here is then equal to this divided by the RMS sort of, I'm going to call it RMS amplitudes, like well, really just the total RMS values of the voltage and the current, not including their phase parts. So what that means is we've got the real power divided by the apparent power. So that's the power factor. Okay, so with that in mind, we can say PF is equal to P over P apparent. And so there's the power factor. It's very close to 1 already, again, because of the very small imaginary component here. Just for fun, if you wanted to change the inductance from 1e minus 3 to 1, then you can make a much higher inductive load here. So now we've got one that's on par, and we end up with a power factor which is lower. So the calculation is actually working out for us. Anyway, if we bring these back to what they were in the problem, 1e minus 3, 1e minus 3. Now we've got our power factor calculated there. And the last thing to do is figure out the capacitance that's necessary to bring the power factor to unity. The capacitance is going to depend on what the load impedance was already. And this is easier to see if we work in admittances. So let's try that this time. Last time we did impedances, so let's try admittances. So what we need is the Y. So what we'll say is that the Y of the load plus Y capacitance, so Y stands for admittance, it's 1 over impedance, has to be completely real. So in other words, we want the imaginary part of this to be equal to 0. And YL is equal to 1 over ZL. YC is equal to J omega C. That's 1 over the impedance of the capacitor. So in this case, we end up with YL 1 over ZL. And we've got the imaginary part of this is negative 5.225 e minus 7. And that means we need omega C to be equal to negative this. So that means C should be equal to negative imaginary part of YL. Let's first just see that that's working. Okay. Negative the imaginary part of YL divided by the frequency. So there we go. There's our capacitance that we're going to need to add in parallel. And now we can check. So we can say ZC is equal to 1 over I times W times C. And Z total, or Z corrected, would be equal to 1 over ZC plus 1 over ZL, and this should be entirely real. So, well, I guess we're running into round-off error there, but we do have certainly a much smaller imaginary component than we had before, now 1e minus 10 rather than to the power of 1. So we've reduced the imaginary part of the load, and that means that with this capacitor added in parallel with this load, we've corrected it. And there you have it. So we can take all of that and whoops, maybe copy this in for people that want to, well, just to keep the code so we've got it for later if we need it. All right, next question. For Number 2, we've got an unknown load plugged into an electrical outlet, which is at 120 volts RMS and 60 hertz. That's the AC line that you've got on the walls there in North America. And it consumes an apparent power of 450 watts with a power factor of 0.5 lagging. We need to figure out the complex real and reactive power, the current, phasor, and the capacitance necessary to correct the power factor. Okay, so we're given the voltage information. So the voltage phasor is 120 volts RMS, and the apparent power, which is the magnitude of the complex power, is 450 watts. And this would be equal to the root of the real power and the reactive power squared and added together. Okay. And another thing that I guess we could say is that we have the power factor there. So the power factor is equal to 0.5, which is the cos of theta v minus theta I. And if we're defining theta v, the phase of the voltage, to be 0, then this is telling us what the phase of the current is. So another thing that this apparent power is equal to is the RMS voltage, VRMS times IRMS. And that tells you that IRMS is equal to 450 watts over 120 volts. And we can figure out what that is. So 450 over 120. IRMS is 450 over 120, and we've got, well, let's evaluate that as a floating point. Okay, 3.75, and that's going to be amps RMS. But if we want to know what the phase is of that, cos negative theta I, which tells us that, so what angle would give you a cosine of 0.5 should be 60 degrees. So theta I is equal to pi by 3. And that means that we've got I. So this is sort of the RMS amplitude, like the, not the phasor, but just the magnitude of it. And we can say what the total phasor is. I guess we need a different symbol. Why don't we call this IRMS, and then we'll put IRMS to be the phasor in Maple here, because we can't really indicate with a bold. So we'll use IRMS multiplied by e to the I times pi by 3. Okay, and then we can say that, so we can check some stuff out. If we've got V is equal to 120, and then we could figure out what the complex power is. S would equal V RMS times conjugate of I RMS. And abs of S, if we've done everything right, should be 450. Great. Now let's check that the power factor is in the right direction. So the power factor is supposed to be lagging, which means the current's supposed to be lagging the voltage. However, here we put a positive number, so that means the current is actually leading the voltage. So we're going to need to modify that to be negative in the exponent there. Okay, so there we go. Now we've got the correct setup here. Yeah, notice as it was last time when we had an inductive load, so the one that would give you a lagging power factor, we have a positive reactive imaginary power there, and that's the same kind that we have here for a lagging power factor. Okay, so we could say I RMS is equal to 3.75 amps RMS times I guess we needed the negative pi by 3. Yeah, e to the j, e to the negative j pi by 3. Yeah, great. Okay, so there is our current phasor. We found the complex power as well. So S ends up being equal to 225 plus 225 root 3 is 389.7 J. And this is going to be in watts and volts amps reactive. Then what else did we need? So complex, real, and reactive power. We need the real power. So the real power would be the real part of the complex power. So that means P is 225 watts, and reactive power, Q, is equal to 389.7 volts amps reactive. Great. The last thing that we need is the capacitance necessary to correct the power factor to unity. And for this thing, we need this is what we needed to know the phase for. Sorry, not the phase. This is what we needed to know the frequency for, because otherwise we can figure out the capacitive impedance necessary, but we can't actually convert that to a capacitance without knowing what the frequency was. So the idea behind correcting the power factor to unity here is that we're going to need to add a current which has the opposite phase of the RMS current that we actually have already. So and is going to be canceling out this part. So what we want is that the current that we're adding is going to be completely imaginary and cancel out the imaginary part of this. So what we need is that this thing is equal to J times, well, let's say it's equal to negative the imaginary part of the RMS that we've got already. And that's, this way it's just going to cancel out the previous current's reactive component. So if that is the current going through the capacitor, then we can figure out the capacitive impedance by saying that the capacitive impedance would have to have been the voltage divided by the current that's going through the capacitor. And then we can convert that to a capacitance by saying the capacitance is equal to, well, let's think. So 1 over j omega c is equal to the capacitive impedance. So why don't we say it like this? And then that tells us that C is equal to 1 over j omega times V with the IC up there. And so we're going to have negative the imaginary part of I RMS times J. Those J's are going to cancel, and this means the capacitance should be negative the imaginary part of the RMS current phasor that we've got going through the load divided by omega times V. All right, let's work all of that out. So that tells us C is equal to negative the imaginary part of I RMS over W times V. Oh, we didn't put in the frequency yet. W is equal to 2 times 3.14159 times 60. And by V here, we really mean the RMS voltage phasor. And we can get rid of the root 3. Okay, so as a check, we can see whether this capacitance actually works by kind of working in the other direction. So ZC would equal 1 over I times W times C, and ZL, so Z maybe original, would equal V divided by, so V RMS divided by I RMS. And then we can find Z new by saying 1 over Z orig, 1 over Z orig plus 1 over ZC, adding the two things in parallel. Let's check. And if we work out what that is, indeed, we have no imaginary component. So it worked. Okay, so again, we ended up with 71.8 microfarads as that, and confirmed that that actually does correct the power factor by bringing the load to be completely real. So to recap, they told us what the RMS voltage was, and they told us what the apparent power was, and the apparent power is the magnitude of the complex power, which allows you to say what the RMS current amplitude is. So the magnitude of the RMS current is, it's 3.75 amps RMS this way, and the power factor of 0.5 is the cosine of the difference in phase. So you work that out and figure out that the current has to be lagging by a phase of pi by 3, which lets you figure out that the total current is this 3.75 amps RMS e to the j negative j pi by 3. And you can work out what the complex power is by either, now that you've got the current, taking voltage times the complex conjugate of the current phasor, or going back to the original idea about what the complex power's magnitude was as the apparent power, and then using the power factor. So with this approach, we got that. We can pick out our real and reactive power, and then we needed to figure out the capacitance necessary to correct the power factor. That comes from the idea that the current going through the capacitor, if it's placed in parallel, must be removing the imaginary part of the current going through the existing load. And this tells you what the capacitive impedance should be, which you can work out to find out the capacitance. And then as a check, we added the capacitance in parallel with the original load. We found the original load by taking the ratio of the voltage and the current phasors, and then we confirmed that this is now completely real, so we've corrected the power factor. Okay, so last part, for the following load impedances, determine the real and apparent power a 1 volt RMS source would provide. So let's check. We've got the impedance and we've got the voltage, and we need to figure out the real and apparent power. So probably the easiest way to do this is to go through the complex power. S is equal to V RMS I RMS conjugate, and I RMS is equal to V RMS over Z, which means that S is equal to V RMS magnitude squared over Z conjugate. Okay, so that means in part A, we've got 1 over 5 minus 2j. So 1 volt squared over 5 minus 2j ohms. And volt squared per ohm should be equal to watts. So 1 divided by 5 minus 2j. We can work that out. 1 over 5 minus 2i is 0.172 plus 0.068690 j. And this is in watts and volt amp reactive. So this is telling us exactly what the real power and the imaginary part is. The imaginary power is to find the apparent power. We can take the magnitude of this. So just converting that same number to polar form, or looking at the absolute value here. We've got the apparent power is magnitude of S is equal to 0.186 watts. Okay. In part B, we do exactly the same stuff, except now we've got 2 minus 5J, and we end up with the imaginary power being equal to 0.0690 watts plus 0.172 volts amps reactive. And this is equal to P plus QJ. And the apparent power, because all we've ended up doing by sort of reversing the sign, that doesn't end up mattering, and switching the switching which was the real and which was the imaginary impedance number, the 5 and the 2, we still end up with a 5 and a 2, so we get the exact same apparent power of 0.186 watts. So a comment on this is these two different loads, one of them is mostly real with a small reactive part, and the other one is mostly reactive with a small real part. This one is the kind of load you would have for an inductor in series with a resistor, and this one you'd have for a capacitor in series with a resistor. The apparent power provided to each of these two different valued loads is identical. However, the actual power consumed is a fair bit higher in the first one. So just by going from the apparent power, you can't tell how much power is consumed. You need to know what the power factor is as well to know whether it's mostly a reactive load or mostly a real load.